Okay, math majors, honest question. When is the last time you picked up one of these? You remember these, right? Compasses? They're these things that you use in high school geometry class to maybe draw a circle or maybe bisect an angle or maybe construct a perpendicular or a parallel line or something like that. It was really cool. You do some stuff with this in maybe 10th or 11th grade or whatever, and then these sort of go away for a while. But I'm here to convince you today that that is a crying shame, because there's a lot that this thing can teach us, not just about geometry, but about abstract algebra as well. Today's topic is the constructible numbers. Those are the numbers, the lengths, if you will, that we can construct using just one of these, a compass, and one of these, a straight edge. Notice this is a straight edge. It doesn't have any markers on it. It's not a ruler. It's just a straight line. You'll have to imagine that it's infinitely long. But nevertheless, we're going to look at the numbers that can be constructed as a length on a piece of paper using just one of these and just one of these. It turns out that those numbers, we call the constructible numbers, form a field, and that field has a lot to teach us about the structure of fields in general, in particular, fields that contain the rational numbers as a subfield. So our objectives are, first of all, to get a working definition of what the constructible numbers are by starting with what I call a Greek tragedy, starting with one of the classic questions in all of mathematics and geometry, and seeing how it was kind of answerable by the Greeks, but then not really. And so we're going to use some more modern techniques to answer a question that the Greeks had some difficulty answering. And that leads us to the definition of the constructible numbers, and it turns out that we can do a lot of arithmetic with constructible numbers, not just addition and subtraction, but also multiplication, division, and one more operation that comes from geometry that makes the field of constructible numbers more interesting than other fields that we might study. And finally, we're going to look at the question of deciding whether or not a given number or given length is constructible with a compass and straight edge or is not, using the tools of field theory, which is what makes this an abstract algebra question. So this really is, as the title suggests, a marriage between classical geometry and the abstract algebra that we're interested in for the purposes of our course. So the classic problem that motivates this question is, can we double a square? In other words, if I have a square drawn on a piece of paper and the area of that square is A, can I, using only a compass and a straight edge, construct another square whose area is twice as large as the first one? Well, again, it depends on what the meaning of the word construct is. And again, construct means that we should be able to do this using only a compass. No, not that kind of compass. I'm talking about the compass we use in high school geometry, one of these things. And a straight edge. And no, not that kind of straight edge. I'm talking about the kind of straight edge that is basically a ruler with no markings on it, which is infinitely long. So we can draw a straight line, but we can't necessarily measure that straight line using it. Well, we can double a square. How do we do it? All we have to do is take our straight edge and lay it down across the diagonal of that square, and then draw another square whose base is on that diagonal. How do we know that this blue square has double the area of the yellow square? All we have to do is observe that it's made up of 4 pieces. Each of those pieces is congruent to each of the others, and one of those pieces is half the area of the original square. So it works. We got 4 pieces, each of which has area A over 2, and so the area of that blue square is indeed 2A. And it turns out that what this implies for our purposes is that we can construct a square whose side length is the original times the square root of 2. Alright, so it works for a square, but what about a cube? Can we do it in 3 dimensions? If I have a cube of starting volume V, can I use a compass and a straight edge to construct a new cube whose volume is twice the original? Well, we could try a couple of approaches like we did with the square. For example, we could try the face diagonal of the cube. In other words, just lay our straight edge across one of the faces and draw the diagonal and construct a cube using that as the side length. But if we do that, we're going to get a cube that's too big. We're going to get not twice the volume, but twice the square root of 2 times the volume. So that doesn't quite work. We could try a different diagonal. We could try the long diagonal that goes from an opposite corner to an opposite corner on this cube. But then the problem gets even worse, because then we end up with a volume that's way too big. So neither of these approaches is enough to double the cube. So it's a valid question. Is this possible at all? I mean, we failed in these two ways, but can we succeed in some other way that we haven't yet found? And that's going to be the question that we hope to answer with field theory by the time that this series of videos is over. So might it be an impossible thing to do to double a cube, to construct a cube with double the volume? So here's our definition. Here's what it's going to mean for a number to be constructible. First of all, the constructible numbers we talk about are going to, first and foremost, be complex numbers. They're going to live in the complex plane. And we call it constructible, a complex number constructible, if we can start with a line segment whose length is equal to 1. So we declare that that starting line segment is equal to 1 length. And then using only a compass and a straight edge, construct that number in the complex plane, beginning with our edge of length 1. So as an example, if this is my edge of length 1, how can I construct the number 3? Well, all I have to do is first extend that line using my straight edge. Then I can use my compass to draw in a circle here of radius 1, and where that circle intersects this line will be a distance of 2 units away. Then I just take that same compass and I draw another circle here beginning from that 2, and by the time I have finished that circle, I can see exactly my length of 3 sitting right there. So we can construct the number 3, beginning from the length of 1, using only a compass and a straight edge. Returning to the question of doubling the area of a square, we can do it because we can construct the number square root of 2, using a compass and a straight edge, starting from the length of 1. All I have to do is start by drawing a circle of radius 1, then extending that 1 into a diameter through the middle of my circle. And then if I just take at the endpoints of that diameter and draw 2 circles of equal radius, if those radii are big enough, then their intersections of those 2 circles connect to form a perpendicular bisector of that diameter. So this is another radius of the circle that's perpendicular to our first. And then connecting that across the diagonal gives me a 45, 45, 90, an isosceles right triangle, and by the Pythagorean theorem, the length of that hypotenuse is the square root of 2. So indeed, we can construct the square root of 2 using a compass and a straight edge, and if we can do that, then that means we can double the area of any square as well. Okay, so we know what constructible numbers are, but what can we do with constructible numbers? Can we do arithmetic? Can we do algebra? What's the structure behind them? And the answer is yes, we can do quite a bit of arithmetic with constructible numbers. First of all, we can add them and we can subtract them. So this proposition says that the constructible numbers are an abelian group with the operation of addition. How do we do that? Well, we can add 2 constructible numbers. If I have k1 and k2, both constructible, all I have to do is take a straight edge and lay out one long line, and then just place k1 and k2 adjacent to one another like this, and the total length that we get there is the sum of k1 and k2. So all I need is a straight edge to construct the sum of 2 constructible numbers. Likewise for the difference. The only thing I do differently here is I lay k1 and k2 on top of one another so that they have one common endpoint, and then the remaining distance that is not covered by k1 but is covered by k2 is the difference, k1 minus k2. And again, we get the abelianness of this group just from the fact that every one of these constructible numbers belongs to the field of complex numbers, and we can take for granted that the complex numbers are an abelian group under the operation of addition. So we don't have to show that addition is commutative here. All we have to know is that the sum and difference of 2 constructible numbers is constructible, and then it follows that they form an abelian group under addition. But the story gets even better. Not only can we add and subtract, we can also multiply and we can also divide, but the construction's a little bit more intricate for that. So let's say I have 2 constructible numbers, k1 and k2. How do I construct, using a compass and a straight edge, the product k1 times k2? This construction is very interesting, and it's going to go by pretty quickly, so this is maybe worth watching a second time if you don't catch it the first time. Here's a tactic we're going to use from geometry. In geometry, the most basic tool that we can use to construct a proportionality is to construct 2 similar triangles. If I can construct 2 similar triangles, then one way of getting k1 times k2 equal to p is to make it so that k1 and k2 are part of the same cross ratio, and then p and 1 are part of the opposite cross ratio. And so what I really need are a couple of triangles where the side k1 in one triangle corresponds to a side of 1 in the other triangle, and in the other triangle, similar triangle, we have a side of p corresponding to a side of k2. So that's going to be the ultimate goal, is to construct similar triangles where I can find those ratios inside of them. Let's start by putting k2 on our straight edge. And then we'll put K1, assuming K1 is the smaller of the two here, we'll put it alongside K2 with a common endpoint on the left side. Then from there I'll construct a perpendicular at the point where K1 ends and the rest of K2 begins. So I have a perpendicular right there. Then remember, every constructible number starts with this unit length. So I can take this unit length and put it back at the beginning, at the left side of K1, and then construct a perpendicular at the end of that as well. So now I have three lengths on here, 1, K1, and K2, all of those originating from the same point on the left, and I have a pair of perpendiculars going up at the end of 1 at the end of K1. Now what I'm going to do is just draw any old line, any old angle that I want to, beginning from the left-hand endpoint and going upwards and to the right. Then, from there, I'm going to connect the point where our perpendicular on the left intersects that line. I'm going to connect that out to K2. So now I have a big triangle whose bottom edge is equal to K2. And then, from there, I'm going to construct another line that's parallel to the one that we just constructed. And it's going to go all the way out here to the edge. And when I extend the line going through 1, K1, and K2, out to there and get an intersection, I'm going to call that P. And my claim is that that P that we just drew in has a length that's equal to the product of K1 and K2. And notice what our similar triangles are here. We have a pink triangle and a blue triangle. And they're going to be similar one to another because they have parallel sides, and therefore their angles are all congruent one to another. And that same relationship that unites the horizontal sides here, P to K2, will be the relationship that relates the corresponding smaller sides, K1 to 1, in those two triangles. And so that gives us the ratio that we were looking for that gives us similar triangles. That probably went by pretty quickly, but it's really an elegant construction, and a completely analogous construction shows how in addition to constructing the product of K1 and K2, we can also construct the quotient of K1 and K2. And as long as K2 is not equal to 0, the fact that we can do this demonstrates that constructible numbers form a division ring. In other words, we can divide by everything except for 0. That, combined with the fact that multiplication of complex numbers is commutative, shows that the constructible numbers, in fact, form a field. We can add, we can subtract, we can multiply, we can divide, and all the addition and multiplication operations are commutative. We can divide by everything except 0. So far, we know that the constructible numbers form a field. What we'll see next is that that field has one additional property that really puts the constructible numbers over the top on the interestingness scale, and we'll see that in the next video.